This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Our speaker today is Dror Baron from Rice University, or at least from Rice at the moment, soon to change. He's going to talk about measurements versus compressed sensing from meets information technology. The problem, as he will explain, is what do you do with all of the information you get from a large collection of sensors. He received a BS and a Master of Science degree from the Technion in Israel, a PhD from the University of Illinois, which he chose over Stanford. And, well, that's all right, you know, people do things like that. He worked for Whitcomb and did design modems. He was a research assistant at the University of Illinois in Champaign-Urbana, where he was also a visiting assistant professor in EE and CS. And since 2003, he's been doing postdoctoral work at Rice University, where this work was done. So without further ado,
okay, Dennis, thank you very much. First, thanks to Dennis for inviting me over. I'd also like to encourage the audience to ask questions. Feel free to interrupt. As long as no physical violence occurs, that's completely fine. And the talk is really going to be about, mostly about compressed sensing, which is a new emerging field, which I will soon describe. And compressed sensing has a lot of relationships to other fields, and I really have a lot of background in information theory, and I'll tell you about a lot of the interactions between these fields and how mutual insights can give us new understanding. So the traditional way how in the DSP community, digital signal processing, the traditional way how we acquire and process signals is that we begin with some analog signal, which we denote by X, and X is then sampled n times. And that is a uniform sampling along some type of grid. And after we sample the signal, we compress it. And compression really means, in many cases, taking inner product of the signal relative to some transform where that signal happens to be represented compactly, only a few of the coefficients will be large, and then you only really transmit, store, keep the k largest coefficients. All the rest of them are thrown away. And those k largest ones contain most of the interesting information about the signal. That's the encoder side, which is pretty heavy on computation because you need to compute all of these transform coefficients. In contrast, the receiver side is rather lightweight. We take the k numbers, form a linear combination of the k transform vectors that they correspond to, and that's x hat, our approximation to the signal. So not only is most of the action happening on the encoder side, most of the action in terms of computation, power consumption, additionally, in some modern acquisition systems, there's starting to be a problem nowadays because we want to acquire signals with a very high bandwidth, and the analog to digital converters simply aren't fast enough. So there are some challenges that are arising. Now, the reason why this whole thing has worked so well for several decades is because a lot of signals are sparse or compressible relative to some representation. So if we take this image, which happens to be in yet another university, MIT, if you'll notice in the distance, and we observe the wavelet coefficients of this image on this side, and you'll see that most of the coefficients are dark blue. They're very small in magnitude. Only a small proportion of coefficients suffice to describe that image rather well. This is a bat chirp, which you can see it has a lot of bandwidth. But if you try to describe it in an appropriately chosen Gabor basis, once again, just a small number, k, of coefficients captures most of the information in a signal. Now, really, if you think about Shannon's sampling theorem or Nyquist's sampling theorem, these are worst-case bounds for the class of all band-limited signals. They say that if you have a signal that the frequencies in that signal are up to b, and you sample it at 2b, then you can later reconstruct that signal. Unfortunately, the class of band-limited signals is very broad. There are a lot of signals where really the information is contained in a much smaller subspace. And these sampling theorems are somewhat pessimistic for those types of signals. They don't really exploit the fact that the signal is lying in a much smaller subspace. And what ideally we would like to do is to directly sense the compressible information at the information rate. That's where this new emerging field of compressed sensing comes in. It's based on the rather surprising revelation that sparse signals can be recovered from a small number of linear measurements where the measurement rate is related to what we call the information rate. Now, Candace and Donahoe have done a lot of work in the last 2-3 years, which has given rise to this field, but actually the mathematical groundwork was laid down by people like Cashin and Gluskin in the 70s. And the ideas that have really led to this whole field crystallizing is based on some new uncertainty principles that go beyond Heisenberg's relationship between time and frequency. So we now have incoherency properties that relate between pairs of bases. These are two different bases. This basis contains spikes. Each of the columns of the matrix, this is a matrix, not an image, each of the columns contains one spike inside it. And if you'll try to represent that spike using the sinusoidal columns of that basis, then basically you're going to need all of the sinusoids to put together each of the spikes. And therefore, anything that's sparse in the spike domain, it can be represented well with only a few spikes. You're going to need a lot of sinusoids to represent it in the sinusoidal domain, in the Fourier domain. Similarly, anything that contains just a few frequencies, you're going to need a lot of spikes to represent it well in the spike domain. So these two bases are incoherent. Similarly, take any deterministic basis on this side, and then try to represent a signal which is sparse with that deterministic basis, with another basis which basically consists of white noise. Okay? So this is a white noise basis, and you happen to be sparse in spikes or sinusoids or whatever. And with probability 1, your white noise basis representation will not be sparse. And these types of properties are leading to some interesting new things, and as you'll soon see. What compressed sensing really does, it works through a startling idea of random projections. You take the signal x, and you take projections, linear projections of the signal relative to these white noise vectors. And once you've taken these m projections, where m is mildly larger than k, like k log n over k, those m projections enable you later to reconstruct the signal. Now, what's important to note is that the number of measurements is only somewhat larger than k, yet on the reconstruction side, we have an optimization routine which enables us to capture the signal, although we don't really know which of the k coefficients were large. Any k out of the n could be the big ones. And that's the interesting property here. Now, another interesting property is that this is also a highly asymmetric system. In contrast to the DSP paradigm from before, where the encoder was running a lot of computation, here the encoder is only taking these m random projections. That's it. In contrast, on the reconstruction side, we're using an optimization algorithm where things could be a bit more interesting. Any questions?
it just source coding?
Not really, because you need the reconstruction side is not really source coding. Source coding really consists of.
Source coding is the processing of the source.
Excuse me?
Source coding has to do with encoding the source in an efficient way from an information
Well,
theory
this is
point of view.
this is
That
somewhat.
has to be unavoidable in the receiver, but
Let's actually take the question offline.
okay.
Now, the compressed sensing encoding, we have a signal x, which is again of length n, and they're going to keep things as simple as possible. I'm going to assume that it's sparse in the time domain, meaning that there are k blue boxes where that signal is non-zero, and the rest of the signal will be 0. Again, this is a simplification just to keep things simple. We encode or measure the signal by multiplying x by the measurement matrix phi. Phi has m rows and n columns, far fewer rows and columns, and that's why the measurements, the number of measurements will be much smaller than the length of the signal. Okay? Now, what's important to point out is that this measurement, the matrix vector multiplication, can actually be performed in analog. And the reason why that's important, if you actually ran this on a computer by calculating inner products, then you would need to sample all the n samples of the signal. That's not what we want to do. We want to actually reduce the number of measurements that are taken. And to do so, we take these m random projections in analog. And we'll later see how that can be done. And once again, random projections. And the reason why the measurement matrix phi will be a random measurement matrix is because we have this property of universal incoherence. Any basis in which our data is expected to be sparse in, our random measurements will be incoherent with that basis, and that will enable us to reconstruct the signal. So I've been mentioning reconstruction, and how do we actually go about reconstructing a signal? Well, we have the measurements, y equals phi x, and we obviously want whatever we reconstruct to satisfy the measurements. Unfortunately, as I've mentioned, the number of rows is much smaller than the number of columns. And therefore, this is really an ill-posed problem. We have infinitely many solutions to these constraints. Actually, there's an entire subspace of solutions that satisfy y equals phi x. Now, yes. So the traditional signal processing approach to this type of problem is to take a least squares solution. In the subspace of explanations to the measurements, we take the explanation that has the smallest energy. Now, it so happens that this solution can be calculated in closed form using a pseudo-inverse. That's good news. But unfortunately, a small amount of energy does not imply sparsity, and we're going to get the wrong answer. What is really happening here is that we are interested in a signal that happens to be sparse. The number of non-zero coefficients is small, and that doesn't really coincide. That's not the right metric to use. Energy is not the right metric. Instead, what we would ideally like to do is minimize the number of non-zero entries in the space of solutions, explanations to the measurements. This is the ideal solution. And it so happens that if the data was k sparse, then it can be shown that k measurements do not suffice, but k plus 1 measurements enable perfect reconstruction with probability 1. So one measurement really separates the impossible and the possible. Well, this sounds like a beautiful result. But first of all, it's not robust to things like measurement noise, all kinds of tiny additional coefficients. And furthermore, this reconstruction really involves combinatorial complexity because we need to search over all sets of k columns out of n. So this looks very elegant and beautiful, but not going to work. What is really the revelation of compressed sensing? It's the usage of an L1 minimization. You look for the explanation to the measurements in this space that has the smallest L1 norm, and it so happens that taking k log n over k measurements gives you perfect reconstruction with high probability. Additionally, in contrast to the L0 reconstruction, which I've just identified as an elegant but faulty procedure, here the L1 reconstruction is robust to measurement noise, robust to all kinds of slight inaccuracies in the model, and it can be computed using a linear programming routine, which is, of course, computationally tractable. So compressed sensing definitely has many advantages. It changes the way how we can think of signal acquisition as long as we have some side information that the signal happens to be sparse in some basis. Now, on the hardware side, we have a very nice feature of universality. Because we have universal incoherence, all we really need are to take random projections of our signal. And this will really suffice no matter which basis we happen to be sparse in. We have one set of hardware for any compressible signal class. Compressible signal class meaning any basis. So we have one hardware design, one algorithm design. That's it. Now, on the processing side, the software or DSP side, we also have interesting advantages. Basically, these random projections are similar to sufficient statistics. And therefore, if you take more or less random projections, you can perform different types of tasks. On the high end, if you have a lot of random projections, you can perform signal reconstruction at a good quality. If you have less random projections, maybe you can only estimate something or perform detection. There's basically here a notion of information scalability. The more measurements you have, the more you can do. Now, based on these types of ideas, we've done all types of different research problems. One of them is along the lines of how do you actually capture these random projections in analog. That's what I'll describe briefly. I'll then get onto the main part of the talk, which is really the relationships between compressed sensing and information theory. Yes, Dennis.
Critical to all of this is some source of entropy, random number generator of some sort, either analog or digital, and presumably a digital generator.
Yeah, so when we're talking about random projections, what's really happening is that we're always going to have a random number generator that we're going to provide it with a seed, and then the random projections, the entries of the random measurement matrix will be outcomes of that seed.
Right. The question is, how good does that generator have to be?
Well, our numerical experiments have shown that 64-bit random seeds are perfectly fine in basically all the different settings that we've examined. This hasn't been proved formally, but it appears very promising. Okay, any additional questions at this point? Okay.
Well, yeah, actually, at what point does it, so you're talking about using random projection, presumably because it's right? You said it's computationally undesirable to choose intelligent ones, if you will.
No, not necessarily. Actually, the reason why random projections are often chosen is because it so happens that this random measurement matrix has a lot of nice properties and it's easy to prove theorems. Actually, part of the talk, I'll tell you about measurement structures that instead of being this fully Gaussian random measurement matrix, it has a much simpler structure. So there is a significant amount of flexibility. What your measurement matrix structure is, the Gaussian measurement matrix, or let's say Bernoulli, ones and zeros, those happen to have a lot of advantages. They're robust to a lot of different signal classes. If you're willing to back off from the demands of robustness and basically only process a certain type of signals, you can do things that are a lot more ambitious. Okay, so let me continue. Once again, a very important point here is that we're trying to reduce the number of measurements. And we're doing that either because maybe we want to consume less resources, less power, or maybe the analog to digital converter isn't fast enough. But that's one of the main goals, reducing the number of measurements. And it's very important to collect the random projections in analog. Because once again, if we do them in digital, then we need to first acquire the entire signal and then compute the inner products digitally. That's not what we want to do. One way to collect these random projections in analog is with our compressed sensing camera. which actually in the last several weeks it's been receiving a lot of attention, even in some mainstream media. If you think about that projector, maybe not that one specifically, but a lot of these projectors, the way how they work, there's a light bulb, and light is being bounced off an array of small micromirrors, and we're controlling each of the micromirrors which direction it's pointing to. And based on that direction, we can control whether light from a certain pixel will hit a certain location on the screen. So the way how we arrange this nice image is basically controlling these micromirrors. What we do with our compressed sensing camera is actually dual to that. We're taking light from an outside scene and projecting it through a lens onto this array of micromirrors, and then the light is bounced onto a photodiode. Now, by controlling the directions of each of the micromirrors, we're basically determining which of the pixels in the image is being bounced to the photodiode or not, and this enables us to basically accumulate the relevant photons at the photodiode. We then quantize the number of photons that we get and transmit, and that's our entire encoder. Now, it's important to point out that each measurement here, each random projection is going to be one pattern of ones and zeros on this micromirror array. And by alternating over thousands of different patterns on the micromirror array, we get thousands of different random projections, and we transmit all of them and are later able to reconstruct the signal on the DSP side. Now, this is just to demonstrate. These are the first results of our camera from several months back. More recently, we've been looking into different reconstruction routines that have slightly better performance. Here's an original image of size 64 by 64. You can see that it's the letter R. And to keep things in perspective, an ideal system that would be allowed to represent that image using 400 wavelet coefficients would give this type of quality. Now, from a mathematical point of view, what we're doing is well defined. Everything is fine and good, but we are running into problems with the hardware. The image on the micromirror array actually looks like this: fuzzy, noisy, distorted, etc. Now, taking 1,600 random measurements, which is 38% of the number of pixels, this is the image that we're getting. So you can see that it's fuzzy and work needs to be done, but these are the initial beginnings. Another direction which enables us to take random projections in analog is really giving rise to a new type of analog to digital converter. Now, the challenge in these systems is that sometimes we need to process wideband signals. For example, in radar and ultra-wideband communication systems, the signal is often several gigahertz wide. And sampling it at 5 or 10 gigasamples per second is beyond the current state of the art in some applications. What we really suggest to do instead is to take the signal X, modulate it, multiply it by this pseudo-random noise sequence P, apply a low-pass filter, and then sample it at the information rate. Now, the really neat thing that's going on here is that although we're using these very simple hardware components, a modulator, low-pass filter, an analog to digital, which is operating at a much lower frequency, despite that, we're getting good reconstruction performance at measurement rates that are much lower. So these are two specific examples of projects that we have that are actually taking these random projections in analog. I'll now move on to the main part of the talk, which is really, again, the relationship between compressed sensing and information theory. Information theory has provided a lot of results in channel coding, source coding, and we've really been borrowing some of these ideas toward solving compressed sensing problems. The first thing that I'll talk about really relates to answering the question, how many measurements do we need to take? I told you that if we perform compressed sensing reconstruction using L1 minimization, that's basically a linear program, then we need k log n over k measurements. That's a very promising result for signals that are strictly sparse. And it so happens that if we're looking at compressible signals, where we have a few large signal components and the rest of them are non-zero but tiny, in this case, once again, if we want the quality of a k-term approximation, we need k log n over k measurements. And there are nice low complexity, polynomial complexity algorithms that can perform this type of reconstruction. So on the one hand, the good news, k log n over k works, but actually there are results from the 70s that say that we cannot go well below k log n over k. So what's going on here? Is k log n over k some magic number? Well, of course, the fundamental goal here is to reduce the number of measurements. Indeed, Dave Donahoe wrote, and he's a Stanford guy, so he must be right. Why go to... Well, yeah, Department of Statistics, yeah. Why go to so much effort to acquire all the data when most of what we get will be thrown away? So if you have 1 million pixels in your image, why take a million measurements when 980,000 are going to be thrown away? And recall that example that I had earlier. If we have a signal that is exactly k sparse and the rest of the n minus k are precisely 0, in this case, k plus 1 will work. Now, again, it's not robust, combinatorial complexity, but there appears to be some promise in some cases to reduce the number of measurements. Now, the reason why this has been a very complicated problem is that the design space at hand is very rich. The compressed sensing field is new. A lot of different people have attacked it with different ideas. And when we started looking into this problem, how many measurements do we really need, we went through a lot of thinking of what specific angle to attack the problem with. One of the difficulties is that we need to understand what performance metric to use. We're going to reconstruct a signal. And our reconstruction is not going to be perfect. But how do we measure the discrepancy between what we reconstruct and the original signal? Now, Wainwright suggested to look at the support set of the non-zero entries. So basically, you have k locations where you have the non-zero entries, and now we're going to reconstruct those k locations by some k hat locations, and hopefully those k hat new locations are similar to the original k. What this is really alluding to is an L0 distortion metric. The number of places where you got the support set wrong, that's the distortion. Now, unfortunately, suppose that you have a really tiny coefficient and you get it wrong. With this metric, that will cost you just as much if you got a really big coefficient wrong. And intuitively, we feel that we want to get the big coefficients right, and the small coefficients are less important. So maybe L0 is not the best distortion metric. Maybe L1 or L2, something totally else. Maybe L infinity. There are all kinds of different distortion metrics, as the audience knows. Another complication is to understand what reconstruction algorithms are legitimate. Is any reconstruction algorithm legitimate, or maybe only polynomial complexity ones like L1 reconstruction? Or maybe L1 reconstruction, it has cubic complexity, n cubed. Maybe that's not legitimate. Maybe that's too much. Maybe only near linear complexity algorithms are fine. These are various possibilities that we were considering when attacking this problem. And finally, how to account for imprecisions in the model. Noise in the measurements, compressible signal model where we have a bunch of tiny coefficients. All of these different things had to be understood before we had a mathematical setting where we could do our analysis. So let me now present our lower bound on the number of measurements. We really came to the conclusion that in any analog system, when we're going to be collecting those random projections in analog, we're always going to have noise. We're going to have nonlinearities, we're going to have distortions, we're going to have interferences between different signals. It's going to be a mess. And we are always, to keep things simple, we're just assuming Gaussian, additive Gaussian noise in the measurements, the simplest mathematical model. Now, instead of saying that y equals phi x, for this specific problem, we're saying that phi times x equals y0. Y0 are the ideal measurements, and the true measurements are actually phi x plus z. So we're adding the noise component z to y0, and z is going to be a independent and identically distributed Gaussian noise vector. Now, what's very important to point out, this is one way of looking at the problem, that you have a strictly sparse signal multiplied by the measurement matrix plus analog noise in the measurement system. But there's a different perspective. Imagine that you had a lot of tiny coefficients. Well, if you're taking a random projection of a lot of tiny coefficients, the outcome is going to look random. So basically, I'm saying that thinking about a compressible signal where we have a lot of tiny coefficients is similar to thinking about an ideal case sparse signal which is being measured and adding noise. These are two problems that are somewhat related. OK, so in order to make progress and show you the result, let me just make several definitions. First of all, the signal-to-noise ratio. That's the ratio between the energy in the ideal measurements and the energy in the noise. Next, we're going to be using some reconstruction routine, any reconstruction routine, any complexity. And that's going to consist of a decoder mapping, dx, and it'll map y, the non-ideal noisy measurements, to x hat. The reconstruction distortion metric will be called d. That's the ratio between the L2 of the reconstruction error and the L2 of the signal energy. And once again, I'm emphasizing we chose an L2 metric. We could have made other choices. And the main goal, of course, is to minimize the measurement rate delta. Delta is the limit, when we look at large problems, of m over n, the ratio between the number of measurements and the length of the signal, where we consider all dx's, all reconstruction routines subject to a measurement noise SNR. Now that we have all the definitions in place, our main intuition is really realizing that what's going on here is that we have ideal measurements y0 and they're passing through a channel. The measurement process is actually a channel. The input of the channel are the ideal measurements and the output are the noisy measurements. And channels have been characterized a lot in the information theory community. And we happen to know that for an additive white Gaussian noise channel, we have a capacity. A capacity is the maximal number of bits that each measurement can give you. And the capacity of this channel with that SNR is half log 1 plus SNR bits. What I'm telling you is that measurements are bits. Every measurement gives you a certain number of bits. And that amount of information, the number of bits that you accumulate over all the measurements together, that's the information that you have to try to extract something about the signal. This also relates to what I was telling you earlier about information scalability. The more measurements, the more bits, the more information, the more you can do. That's really one of the key insights of the talk. And our lower bound is as follows. You take a sparse signal with rate distortion function R of DL. I'll soon tell you what that means. Then the lower bound on the measurement rate delta, when you are trying to get distortion reconstruction quality D subject to SNR measurement noise, this is the lower bound, what you have in that expression. Now, there are two things that I want to emphasize here. One of them is in the numerator, you're seeing R of D. R of D is the rate distortion content of the source. You have a linear relationship between this information theoretic term, how many bits you need to describe the source, and the number of measurements that are needed in a compressed sensing measurement system. This looks very interesting. And we don't know yet if this bound is tight, but if it will turn out to be tight, or perhaps some other bound with R of D in the numerator, this will basically say that compressed sensing and information theory are really closely tied. Another interesting point is that, once again, this applies to any linear signal acquisition system. Any reconstruction algorithm, any measurement matrix, you can't beat this bound. Let me quickly tell you how we go about proving this. Again, the main insight was that each measurement consists of giving you bits. Measurements are bits. Half log 1 plus SNR bits. Now, the information content of the source is n times R of D bits. What this really means is, if I have a signal of length n, and I want to compress it up to distortion quality D, And I see the entire signal. I know everything. I'm just trying to tell you about the signal. I need n times r of d bits to tell you about the signal at distortion quality d. The next step is the source channel separation theorem of information theory. What that source channel theorem basically says is as follows. Suppose you have any communication system that is looking at a signal and trying to communicate it over a lossy channel. Well, you could do anything, but it turns out that you could not do better than first looking at the signal and compressing it with a rate distortion technique with n times r of d bits, and then communicating those n times r of d bits with a channel coding technique that protects you against problems over the channel. And because of this principle, the source channel separation theorem, the number of measurements, in total it needs to give you n times r of d bits of information, and each of the measurements is only giving you half log 1 plus SNR, and therefore the ratio of the two, that's the lower bound on the number of measurements. And we get the measurement rate by simply normalizing the number of measurements by the size of the problem n. That's the entire proof. Of course, I skipped over a few technical details, but this really gives you the main idea. I'd like to illustrate with some numerical examples. Consider a spike process that basically presents, it produces spikes of uniform size, only ones and zeros. The spikes are always going to be ones. I don't want to deal with the amplitudes. That's just too complicated. And there are going to be k spikes out of n locations, and you need roughly k log n over k bits to describe those locations perfectly. And suppose that you don't really need to do it perfectly. You're willing to absorb some distortion d, so maybe you can do it in 0.8 k log n over k log n over k, or 0.7 k log n over k. But you're not going to be able to do this with a tenth of that. You're going to be kind of like k log n over k bits. The number of bits needed to reproduce this source. Now, the lower bound is telling us that this is the measurement rate which is required. And to put this in perspective, consider a signal of length n equals 10 million with k equals 1,000 spikes, and your measurement process will be fairly clean, 10 dB. In this case, you need roughly 7,700 measurements. And recall that we have 1,000 spikes. So if you need 7,700 measurements to capture 1,000 spikes, that's reasonable. This is definitely compressed sensing, and relative to the length of the signal, 10 million, you're saving several orders of magnitude. It looks beautiful. In contrast, suppose that you have a measurement quality of minus 20 dB. So the measurements are now very noisy. Now you need 1.85 million measurements. Now, on the one hand, 1.85 million is sure better than 10 million. But it's a lot larger than 1,000. And the main point here is that if the interesting portion of the signal has a relatively small energy, then there's not much that you can do. You're going to need a lot of measurements. An interesting portion of the signal can be interpreted in different ways. As I was saying earlier, you can think along the lines of, I have an exactly sparse signal, and I'm having additive white Gaussian noise in the measurements because the analog system has problems. But I can also think about it as I have 1,000 spikes buried inside a signal of length 10 million, and the other 9,900,something thousand coefficients are small, but they're non-zero. And when we project them randomly, we get noise. And that type of problem, if in total they contain 20 dB more energy than the portion of interest of the signal, we're going to need a lot of measurements. That's the main importance of this result. So this is the lower bound, and we're working on an achievable result where basically we're saying there is a reconstruction technique that can do so-and-so using so-and-so number of measurements, and that upper bound is a work in progress. Any questions at this stage? Okay. Next I'll tell you about another direction that we've been looking into, which again exploits some ideas from information theory, and these are ideas from the channel coding community. Basically, we are performing compressed sensing reconstruction using ideas that have been around for channel coding. The reason why the compressed sensing reconstruction requires a significant amount of computation is that if you look at the measurement matrix phi, then that measurement matrix is basically a random measurement matrix, which is dense and unstructured. And therefore, the matrix vector multiplication requires a lot of computation. And actually, not only does the matrix vector multiplication require a lot of computation, the reconstruction routine will iterate over this multiple times. And in total, this will be quite costly. Linear programs, again, are roughly cubic complexity. Now, for problems of size 1,000, this is fine. But for problems of size 1,000,000, I want to see any of you running a true linear program on a problem of size 1,000,000. So how do we overcome that? The compressed sensing way of overcoming that really relies on a channel coding technique called linear density parity check codes. I'm sorry, low density parity check codes. We use a measurement matrix that has these red entries. These are ones, and all the rest are zeros. And furthermore, this is a matrix with a sparse structure. There are not too many red entries. In each of the rows, we only have L red boxes. And because of this structure, the matrix vector multiplication, all of a sudden, it's very simple. All we're really doing, we're adding up the L locations where each of these rows happens to be non-zero. And consequently, the encoding is fast because the matrix vector multiplication is fast, and the reconstruction is fast because we don't need to iterate over this process too many times. The specific technique how we are performing the reconstruction relies on belief propagation, which again has been used in the information theory community to decode channel techniques that relied on LDPC. So basically what's happening is that on the one side of the problem, we have the states. These represent the data, and each of the locations in the data, there is some statistical prior that says what is the probability of being non-zero, and also subject to being non-zero, what's the probability for different types of amplitude. So we have an entire probability density function for each of the locations in the data. On the other side, we have the measurements, and we want the measurements to explain the data. Now, the way how these belief propagation techniques work, you basically iterate. You pass messages between the two sides of the graph. And by iterating, by conveying density functions, you try to eventually converge to an explanation to the measurements, which somehow relies on this prior. To show you that these ideas are actually beneficial, we try to simulate these types of reconstruction routines on signals that look like that. So you have a signal of length 600 with a small number of spikes. And as you can see, the signal was definitely noisy. What I'm illustrating here are results for different L's. L, once again, is the number of ones in each of the rows. And what I'm illustrating is that as the number of measurements increases, the L2 reconstruction error goes down. Now, when I have very few measurements over here, the L2 reconstruction error is basically terrible. The reconstruction error is equal to the noise in the signal. And when I have more and more measurements, eventually the reconstruction error approaches the L2 norm, the energy in the noise. And basically, I can't beat that. And what you can see is that for the different L's, again, the number of ones in each of the rows, I'm getting slightly different characteristics, and part of our ongoing work is to optimize how many ones you need in each of these rows. Now, not only do we have these nice results via simulation, we also have some promising theoretical results. First of all, the complexity is n log n. That's rather modest. And we've proved that using k log n over k measurements, we get a reasonable reconstruction noise. And really what's happening here is that there are a lot of results in the information theory community, both using these LDPC measurement matrices and the belief propagation routines for reconstruction, and we've really borrowed these and applied them to compressed sensing. The last part of the talk will be our work on distributed compressed sensing. Here, in contrast to before, where I had a single signal, here I have basically a sensor network of different signals. This is a distributed signal ensemble. And I'm going to be collecting all of these signals together, but each of them at a different signal node. And we're going to try to reconstruct the entire signal ensemble. Now, the motivation for this problem is because there's been a lot of interest in sensor networks. In this application area, we have a lot of sensor nodes which are dispersed over maybe a large geographical area or a research lab, and together they're collaborating to perform some signal processing task. Each of these nodes has some capabilities built into it. The sensing mechanism, of course, computation, communication, networking, and it also contains a battery. And you can see that the battery is somewhat sizable because power consumption is a bottleneck in these application areas. Now, it's been observed that the communication costs take up a relatively large percentage of the power consumption, and therefore minimizing the communication costs is very important. And that's what really motivates the field of distributed compression. We want to reduce the number of bits that we need to communicate, and that will enable us to reduce the resource consumption. Okay? So the naive way that you would do this would be that you have a bunch of sensors, and they're each picking up these signals, and they're sending raw, uncompressed data toward the destination. This is typically inefficient because we're not compressing. Why can we compress? We can compress because there are all kinds of correlations in the data. This guy is yelling, and these different sensors, each of them individually picks up a signal which has correlations in the time domain. And because of that, each of these sensors can compress individually. But in addition to that, these different sensors, which are located close to one another, they're picking up audio signals that are correlated in a spatial domain. And therefore, we have another domain in which we can compress if we saw the entire signal ensemble and could process it together. And that's really what we'd like to do. We want to somehow exploit these different types of correlations to compress the signal. And I want to point out that it's been an ongoing challenge in the information theory community to exploit both of these types of correlations at once. One way of doing it, one way of handling this type of challenge is basically to collaborate among these sensors. These sensors are going to be picking up the signals, and then they'll communicate to each other some overhead, which will tell them about the structure of the signals at hand. The problem, of course, is that not only will this require a lot of complexity in the sensors, but this communication overhead is costly. It requires to communicate, and it increases the power requirements. What we propose to do instead is to collect these random projections at each of the different sensor nodes, and then to communicate the implicitly compressed measurements toward the destination. And at the destination, we're going to be reconstructing the entire signal ensemble together. What this will enable to do, we're going to be, in the reconstruction routine, we'll use a signal model that incorporates both temporal and spatial correlations, and that will really enable us to address both of those types of correlations together. No overhead, low complexity at the encoders, all of the action will happen at the reconstruction routine. I'm going to present 3 different models for this distributed compressed sensing. In our first model, we have a common component in all of the signals, and in each of the signals we also have a slight innovation component. To motivate this, suppose that we're measuring signals in a smooth field. This could be a temperature field, and we're measuring it here and in San Jose and in San Francisco, and you would expect that the temperature in these different locations will not be too different because the temperatures are driven by some global weather patterns. But of course, in each of these locations, there could be rain and clouds and winds and mists in San Francisco and who knows what else. And there's going to be innovations in these different signals. The way how we model that, we say that x1 and x2, these two length-n vectors, they contain, first of all, the gray common area. We call that ZC, the common component. And they also contain Z1 and Z2. These are the colored areas in x1 and x2. Now, the number of boxes in the common and in two innovation components, we denote that by KC, K1, and K2. And then we measure these two signals, x1 and x2, by multiplying them with these random measurement matrices, phi1 and phi2. And the outcome, the measurement vectors, are y1 and y2. What we'd really like to do is to measure as little as possible. Now, the most naive thing that we could do is to measure using two different encoders, F1 and F2, and to reconstruct using two different decoders, using G1 and G2. That's, the simplest solution. How many measurements do we need in order for this type of thing to work? Well, in the first signal, x1, the number of non-zero boxes is Kc plus K1. Kc boxes for the common, K1 for the innovation. And therefore, the number of measurements that we need to reconstruct x1 needs to account for some log factor, a constant c, times Kc plus K1. So M1, the number of measurements, must be here or beyond. Similarly, the number of measurements to reconstruct the second signal, x2, we need to reconstruct Kc plus K2 non-zero components. Again, we need some log factor times Kc plus K2. So anything in the M1 plane in that area can be done with this approach. But actually, Slepian and Wolf showed in the information theory community a somewhat interesting result. Suppose that you're looking at distributed lossless compression. You have two different encoders, and they're not talking with each other, no collaboration, and you have one decoder, and it's decoding both of them together, joint decoding. What they showed is that when you do separate reconstruction, separate decoding, again we have the box from before, where we need to exceed the entropy for the first source and the entropy for the second source. Those are the rates required, R1 and R2. But all of a sudden, we're reconstructing the two signals together, a joint reconstruction. And Slepian and Wolf showed that you have this entire additional area where things can happen. Basically, individually, each of the rates, R1 and R2, only need to exceed the conditional entropy, conditioned on if the other guy was known. And the sum of the rates only needs to exceed the joint entropy. So less bits are needed. What we'd really like to do, inspired by the Slepian-Wolf coding, we'd like to show a similar measurement rate region for distributed compressed sensing. Instead of constant times Kc plus K1 and a similar term for M2, the number of measurements to reconstruct the second signal, we'd like to show that fewer measurements are needed if we have a single reconstruction box. Well, we did all types of work, both numerical and theoretical, and instead of telling you about the details, I'll just summarize all of our results in this one plot. What we see here, the dotted purple line, those are the number of measurements, the measurement rates that we would need to obtain separate reconstruction, two different reconstruction boxes. We would need to exceed this level for M1 in order to reconstruct the first signal, and we would need to exceed this level in order to reconstruct the second signal. Now, if you look at that corner of the measurement rate region, those are a lot of measurements. We want to measure less. How many measurements do we actually need? Well, we have the solid blue line, and that's a converse result, a lower bound. It says that anything below in this area is not going to succeed, no matter what reconstruction routine that you want. Okay? Now we also have this dash-dotted red line, which is unachievable. It says that we have an algorithm that can actually achieve those measurement rates. And note that this area between the purple and the blue, this is an area where basically things which used to be impossible, once we're reconstructing the two signals jointly together, now these lower measurement rates can be used. So this is good news. Additionally, we have simulation results using a different algorithm from our theoretical achievable scheme. And that algorithm gives us these simulation results, the black circles. And you'll note that here, the black circle is slightly better than the theoretical result. And in the corners, here and here, again, the black circles are slightly better. What I'm really telling you is that the achievable can be improved. So clearly there's a gap between the blue and the red, and maybe we can reduce that gap in future work and get a better characterization of what's going on here. But for now, we leave this for future work. Another thing that I'd like to demonstrate is that as we increase the number of sensors, we can do even better. We can use even fewer measurements. Here, I took a setting where the number of sensors went up to 10. Now, in the previous plot, I told you that when I went from 1 to 2 signals, when I did joint reconstruction of 2 signals, the measurement rate went down from maybe 0.63 to 0.48. And when I added more and more signals, the measurement rates continued going down. And it's worthwhile pointing out that for this specific problem, the lower bound, when the number of sensors goes up to infinity, the lower bound is 0.23. So I'm starting to get reasonably close to that 0.23 when I went to the level of 5 or 6 signals. So these are very good news. There's a lot of potential here to reduce the number of measurements. That really summarizes our first model for a joint sparsity structure. We had a common component and innovation components. I'll now go on to 2 additional models, which I'll go through briefly. In the second model, we have common sparse supports. Suppose that you have a car which is driving around, and it's creating an audio signal which happens to be sparse in the Fourier domain. There are only going to be a few frequencies where the car is creating a lot of audio energy. Now, these different frequencies are being picked up by a lot of different sensors, and each of the sensors is basically picking up the same frequencies. However, because the locations are different, those frequencies are attenuated differently. There are delays, which are different delays. So basically, the Fourier coefficients are going to have different phases and different magnitudes. Motivated by this type of problem, we came up with a model where we have these different signals, x1, x2, up to xj, and the colored areas lie in the same locations. The support sets of where we have non-zero coefficients are the same. However, the coefficient values are actually different. Each of the different sensors is going to pick up these audio signals that have different magnitudes and phases. What we'd like to do, ideally, is to measure each of them separately. Each of the sensors is going to pick them up separately, and the reconstruction is going to be joint. We're reconstructing the entire signal ensemble together using fewer measurements per sensor. The reason why we hope to have some success is that each measurement vector holds some clues about the support set, and the support set is common to everybody. We have some preliminary theoretical results here. First of all, using k measurements per sensor, that's not enough. And secondly, if you increase the number of sensors, j, and you fix the size of the problem, you fix k, the number of boxes per signal, and you fix n, the length of each signal, then in this case, k plus 1 measurements per signal suffice. Now, furthermore, we happen to have joint reconstruction routines that have quadratic complexity. So these are encouraging news. One additional measurement, quadratic complexity, can be done. And to illustrate what we have here we have different reconstruction routines using different numbers of sensors. We have both joint and separate reconstruction. On this axis, I'm plotting the number of measurements per signal, m. We have a signal of length 50. And on this axis, this is the probability of perfect reconstruction over thousands and thousands of simulation runs. Now, of course, as we increase the number of measurements, the probability of reconstruction goes up. That kind of makes sense. But the main point of interest here is that the 1, that means that you're looking at only one sensor. When you're increasing the number of sensors in the direction of the dashed lines, separate reconstruction, every single sensor you pick it up and decode it with a different box, then you need more and more measurements to get a high probability of reconstruction. You need to go in that direction to get a high probability of reconstruction. Now, the reason why this is happening, if I want to reconstruct 32 signals, and I want the entire ensemble to be reconstructed at 50% probability of success, that means that each of the signals individually needs to be reconstructed at like 98%, which is, for one signal, that's way over here. Separate reconstruction is bad for a large signal ensemble. But joint reconstruction is good because, again, I'm getting these clues on the common sparse support sets. And when I increase the number of sensors, I need fewer measurements. Now, actually, here, the length of the signals is 50, and the number of non-zero coefficients is 5. So our lower bound tells us that you could not do 5, and with 6 measurements, we're getting a very high probability of good reconstruction. So this is, once again, this is very encouraging. I also want to present results that we have on real data. These are light measurements at the Intel Berkeley lab. They relied on 49 sensors that picked up 1,024 light measurements each during a period of several days. And if you just look at the signal ensemble, when you're going in this direction in the time domain, these are light measurements. So this could be maybe Thursday and Friday. And you'll see that the activity of the different light sensors was kind of correlated. And here during the weekend, less people came to the office. So there was less light, I guess. Now we're going to compare 3 different reconstruction techniques. One of them is a wavelet approximation using 100 terms per sensor. So 100 out of 1,000. The second method is separate compressed sensing, where we measure each of the signals 400 times instead of 1,000. And then we run compressed sensing in a separate way on the signal. And the third is a joint compressed sensing reconstruction technique that relies on simultaneous orthogonal matching pursuit. Once again, we took 400 measurements. Now, this is the original signal of light node number 19. And you'll note that on Saturday, there was a lot of high-frequency information in that signal. And the 100-term wavelet approximation, it didn't really capture some of those high frequencies well. Now, the separate compressed sensing, you see that there are a lot of these spikes even in the middle of the night when actually things were very nicely behaved. So the separate compressed sensing reconstruction doesn't work very well either. But the joint reconstruction captures a lot of the high-frequency components, not to mention that the SNR is much better than the other methods. So once again, instead of taking 1,024 measurements per each of the signals, I only took 400, and by reconstructing all of them together, I got this promising result. Our third and final model for joint sparsity involves a common component which is not sparse. As an application, you can think, for example, of video. If I'm considering the video of this talk, each of the images individually, maybe it's not very sparse. You would need a lot of bits to encode that image. But if you look at the differences between successive frames, those differences could be very minute. The differences, the motion vectors, would be very sparse. So basically, I have this common component. It's common to all of the different J signals. And that common gray component is not sparse at all. You would need all of the coefficients in order to describe it. And therefore, compressed sensing simply will not work if you want to capture that common component. You can't reduce the number of measurements. However, the innovations, in my example, the motion vectors, are very sparse. And the innovations, maybe they have the same support set, such as our second model, or maybe not. We have different variations on this theme, but basically the innovations are very sparse. What we'd like to do is, once again, to measure each of these separately and to reconstruct them jointly. And we'd like to do that using a reduced number of measurements where hopefully each measurement vector will contain clues about the common component. Here we see an example where we go from 8 sensors to 16 to 32. This graph has a similar structure to before, where these are the number of measurements per signal. And as we increase the number of measurements, the probability that the reconstruction works well goes up. Now, furthermore, when we increase the number of sensors from 8 to 32, we need less measurements. So basically, the bottom line from this result is that the impact of the non-sparse common component basically vanishes as the number of sensors increases. So that really concludes the talk. As I told you before, compressed sensing is really a very, very interesting new emerging field which has all kinds of opportunities. It tells us that these random projections can really be used to do all kinds of crazy things. We can process sparse signals using far fewer measurements in a universal way using the same hardware. And additionally, we have the neat feature of information scalability. You take more measurements, I can give you better reconstruction, or I can give you more answers to questions that you may have about the signal. Now, we described, to begin with, two different directions, the compressed sensing camera and the analog to digital converter, two directions where we can actually acquire these random projections in analog. And then I moved on to the main part of the talk, where I described three directions of work in which we've really related between compressed sensing and information theory. First of all, I started with our rather recent work of providing bounds on the measurement rates that are required in compressed sensing. And the main insight there was that measurements are bits. We have an ideal measurement which is going through a channel, and the actual measurement is corrupted, and we can only extract a small number of bits of, so to speak, information about the signal. And that led to a lower bound on the measurement rate, and that lower bound contains a direct relationship to rate distortion. So basically, the more bits that you need to describe the source at a certain level of fidelity, the more measurements you're going to need in a compressed sensing system. The second part of the work really relied on these different results in the channel coding community, and that's how we performed compressed sensing reconstruction. Again, the results were very promising both from a numerical point of view, and there were also some theoretical results. The last direction where we showed some relationships to information theory was really related to distributed compression and distributed signal processing. I presented three different models for joint sparsity, and for the first model, I had a measurement rate region that had an analogy to the Slepian-Wolf coding theorem of information theory. Basically, once again, by reconstructing jointly, I succeeded in reducing the measurement rates that I needed for each of the different sensors. Now, really, at a broader level, what the distributed compressed sensing offers, it exploits both the temporal and the spatial correlations, because everything that I need to know about the signal ensemble and the statistics in it, all of that knowledge is incorporated in the reconstruction. I take these random projections, which once again, they're similar to sufficient statistics, and those sufficient statistics are exploited in the reconstruction. In the big picture, of course, there's a lot of potential, but also there's much more to be done. And really, I hope that I've showed you that compressed sensing, in some sense, has met information theory, and these relationships between the different fields can hopefully bring us additional success. We have a lot of papers available on our webpage. We basically are accumulating papers from the compressed sensing community. People who have papers in this field are sending them to us, and we're glad to post them online. Feel free to browse this webpage or to send me an email if you'd like any additional information. Thank you very much, and I'll be glad to entertain any questions that you may have. Yes?
I have a question. Analog measurements are not very accurate.
Right.
And so they're sort of bounded by 1% error. So the signal that you're talking about here was an analog representation of a digital signal, or the analog signal itself, per se?
Well, ideally, what's going on is that we have an analog signal, and we want to acquire that analog signal. The way how we model that analog signal, we're saying that we have n numbers. The signal is a vector of length n, and these are, of course, real numbers, and now we want to acquire that signal. The acquisition process, of course, the actual measurements are, as you said, analog and noisy. Some parts of the talk I was taking into account the fact that the measurements are noisy. Other parts of the talk I was talking about perfect reconstruction in an idealized setting where the measurements are perfect. Because, different parts of the talk use different assumptions. Okay. More questions? Yes. You had a question?
Can you get any, has anybody done any work on taking advantage of a reverse channel so that the central node that's collecting all this information can give some hints that might be useful for the compression?
Okay, if I understand correctly, you're saying that the central node will relay information back to the sensors, which will help them measure less?
Or compress better, or...
Feedback channels.
Yeah.
Intuitively, that makes sense. I haven't really considered that in detail, so I can't really give you a real answer.
Doesn't help the channel capacity, but the
No, it
complexity.
doesn't change the channel capacity.
Helps the
Well,
reducing
no,
complexity
but you see,
of the
in the distributed framework, I think that it could help because
Not in the information theoretic capacity sense.
not.
But in a loop of estimation, yes, it can improve.
I think it can help you. It can help you basically converge the statistics faster, and it can, for finite-sized problems, it can definitely help. In asymptotically sized problems, probably not. No, yeah, again, so for asymptotic problems, it's not going to help. Now, I'm assuming that if you look at actual data, actual data is non-stationary. So for actual data, I'm assuming that in practice, it could help. Because in actual data, all the asymptotics don't really kick in. Okay, more questions?
So what's the impact, I guess the most practical application of sensing today has really two sides to it. You've addressed one of them. I'm wondering if there's something that might fit into the other side as well. An individual sensor produces a large amount of information, but what people begin to use in large quantities now are large arrays of sensors where they're looking at spatial distributions of the same measurements. And the question is, how do you reduce the quantity of information to something that's manageable? I know of one project that's building a biological sensor where the actual data obtained is in the order of a few hundred terabytes per second, and it's difficult to find a disk that can take that much information for post-processing. So it has to be sort of done on the fly, and in some sense your sampling technique here, which is fundamental to dropping the quantity of information, is pre-processing the signal, looking for particular pieces of information.
So I just want to understand, before addressing your question, I want to understand. You're saying that on the one hand, you have the data acquisition part, and on the other hand, you have the issue of processing less. Is that the second part that you were discussing?
So that's one of the techniques you're using to decrease the amount of information. So is there an equivalent trick for the distribution, for a distributed array of sensors as opposed to a single, gathering all of the information and doing that separation or collection in one separate place? It's sort of related to the earlier question in the sense that a channel which is describing redundancies passed to the sensors might drop the quantity of information that needs to be worked on. On the other hand, that means sending the n-squared signals back to each individual sensor for some sort of correlation.
So
that strikes me as not being a good bet.
Our work has really assumed that the measurements are going to be accumulated in one location, and that then at that location you're going to basically throw a lot of computational power at it and reconstruct the entire ensemble. What you could do instead, you could have a hierarchical scheme where each 4 or 5 different sensors, you're going to reconstruct them kind of together in a fuzzy way, and you have these super clusters of 5 or 6 of these groups of 5 or 6 where you're kind of, so there, I imagine that you could do these types of schemes where each of these nodes individually wouldn't be processing too much, but as a whole, the system would be kind of sparse, and the measurements, the number of measurements needed would be much lower than what you have today. But this is again the kind of thing which belongs to future work, and I haven't really considered in detail. Okay.
Anybody else? Okay, well, thank you very much. I don't want to.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.